Okay, we're supposed to conduct and interpret a chi-square goodness of fit test. So manufacturers are testing a die to make sure that it is fair, that it has a uniform distribution. So they're rolling the die. They take all these dice in the factory, they roll it, and they're rolling it 66 times, and they record the outcomes below. So we're doing a chi-square goodness of fit test to see if our dice is close enough to the expected value. And look, there's some pretty significant deviations. This one's 5 away, this one's 9 away, this one's 6 away. So maybe it just happened by random chance. Maybe those differences happened just because we got unlucky with the dice. Or maybe they're so far different than the expected value, then we should claim that we should reject the null hypothesis and claim that there's a difference. Okay? So we're supposed to first select the correct null and alternative hypotheses for this test. So with the chi-squared goodness of fit test, the null hypothesis is that everything matches what we originally thought. Like the dice is uniformly distributed. Okay. So remember the null hypotheses that we did earlier in the course. The null hypothesis is that there's the no effect model. There's nothing different than what we expected. So since they're expecting it to be a uniform distribution, the null hypothesis is going to be yes, our values match that distribution. And the alternative to that would be that the die does not have a uniform distribution. Okay? We're looking to find evidence to reject the hypothesis that it's a uniform distribution. Okay, so now we're supposed to compute the test statistic, which I have the formula already on the board here on the right. So to compute the test statistic, this is the poorly drawn, I guess, summation symbol. That means you're supposed to add up all the possible options here in this formula. So we need to take each observed value, so my first one is 16, subtract it by the expected value, square that, then divide it by the expected value. That's for the first column there. Now we have to do it for the next column. We have to do the observed minus the expected squared divided by the expected, and then keep going until you filled out all those columns. We're going to just do that real quick with a calculator because I think the process, once you do the first two steps, it's just the same thing over and over again. Okay, so for that first one, I've got 25 divided by 11. I'll write out these decimals so you could follow along too if you're having trouble with the calculation part. Here's my first one. Second one, I've got 36 divided by 11, 3.27. Third one, it's going to be 4 in the numerator, so we got 0.3636. And same thing on the top for the fourth column. 9 minus 11 is negative 2. Negative 2 squared is 4. Oops, do I have that right? It's 4 divided by 11, not 2 divided by 11. Yeah, okay. Where are we on the fifth column now? That's 16 in the numerator when we square it. So 1.4545. And then the last one, 20 subtracted by 11 makes 9. 9 squared makes 81. And 81 divided by 11 gives us 7.3636. Okay, so now we're doing the summation part. That's why I put plus symbols. We add them all up, okay? In case you're wondering where these came from again, the first 2.2727 was when I did this part in the calculator, the 16 minus 11 squared, then divide by 11. Okay, so I did do that kind of quickly. Let's see if we got it. Rounded 3 decimal places, I got 15.091. Okay, and so that's our test statistic. And just like with other hypothesis tests, we have to compare that to a critical value. So the degrees of freedom when you're talking about a goodness of fit test, okay, it's similar to what you would do with other chi-square test statistics. Normally it's the number of rows minus 1 subtracted by the number of columns minus 1 because those are your variables, the sample size for each variable. Sorry, not the sample size, the number of different options for each variable. It's similar to that idea. Just make sure that you don't include the outcome when you think about that. In short, okay, the degrees of freedom is the number of columns subtracted by 1 here. Okay, because there's 6 columns, there's 6 samples, and if you there's 6 different outcomes, I should say. So 6 subtracted by 1 makes 5 degrees of freedom. So if you look at 5, and then we need an alpha here because it could, 5 is the degrees of freedom, but there's several options in our table. They said the 5% significance level. So remember, chi-squared test statistics are always right-tailed tests. So we just want chi of 0.05, and if you match that up with the 5 degrees of freedom, you got 11.070 for our critical value. And then just like always, you compare the test statistic to the critical value. And since our test statistic is over, here's it's like 15.091, 15 roughly. Our critical value was 11. So our test statistic is in that rejection region. We should reject HO. At the 5% significant level, there is significant evidence to conclude that the die is not fair. Because if you go back to our null and alternative hypotheses, the null hypothesis was that the die was fair, makes a uniform distribution. The alternative is that the die is not fair, that it does not follow the uniform distribution. So thanks to statistics, we can be pretty certain that the die is doing something wrong.